So this is just a series of podcasts on South Asian monsoon extremes, but I will include some papers discussing the general scaling of total precipitation with respect to warming in terms of sensitivity. So percentage precipitation change with each Kelvin warming, and try to compare how that relates to what we expect from Clausius-Clapeyron in terms of 7% increase in saturation vapor pressure with each degree of warming. And then we will try to get into scaling, similar scaling arguments for extreme precipitation increase. So we will see the difference of how total precipitation can be constrained versus how we can think of the extreme precipitation changes in response to warming. Of course, the warming is coming from the radiative perturbations created by human activities since Industrial Revolution. We won't get into the debate about natural variability versus solar activities and trends, but there is plenty of evidence now that we can detect a anthropogenic signal very clearly. And the important thing also for precipitation and precipitation extremes, of course, for the warming is the radiative forcing. So we are looking here at the IPCC AR4 result. So this is from the Intergovernmental Panel on Climate Change, released in 2014 from the chapter Physical Science Basis, a summary for policymakers, right? So we are looking at the anthropogenic timescale since 1750, and here is the zero line, and we are looking at natural solar irradiance change, which is of course a well-known signal, and it is there and cannot explain the observed warming since then. So the level of scientific understanding shown here shows medium, very high, and then there are some that are low, like cloud adjustments from aerosols and so on. Looking at the radiation forcing from well-mixed greenhouse gases, we have CO2, the dominant greenhouse gas, methane, halocarbons, and N2O. And you can see the numbers here. The confidence in these is high or very high, ranging from 1.68 watts per meter squared, but of course with a large range. And similarly for methane and other greenhouse gases, well-mixed greenhouse gases. There are short-lived gases and aerosols like carbon monoxide, non-methane volatile organic compounds, NOx, aerosols, precursors, cloud adjustments, and so on. These numbers are much smaller, and the confidence is high for aerosols, but not so high for the others. Others include albedo change related to land use, contrails, HFCs, PFCs, and SF6. But in total, anthropogenic forcing in 2011 relative to 1750 is over 2 watts per meter squared, with this range from 1.13 to 3.33, and the overall confidence on this is very high. So we have to translate this radiative forcing with the known temperature changes and the pattern of temperature change to precipitation changes and the pattern of precipitation change. Of course, when you look at precipitation, you have to look at duration, intensity, and frequency, and out of that precipitation you also have to look for changes in extreme precipitation. So we'll start by looking at a very brief introduction to the South Asian monsoon, which will be the main focus for the extremes. I'm taking these from Goswami's chapter from the Lau and Walliser book on intraseasonal oscillations. As you can imagine, probably you already seen these. This is for December, January, February, showing rainfall when the sun is to the south, the ITCZ is to the south. There is some rainfall to the north, of course. Some parts of India do get northeast monsoon, and the summer season, which is what we will mostly focus on, has this kind of a complicated pattern over India, where sun is to the north, land heats faster because its heat capacity is lower, ocean heats lower. So we will mention the debate about the role of the ocean land thermal contrast for driving the monsoons. But once the monsoon is set up, you can see the pattern. There is a precipitation maximum here. There's the Western Ghats here, of course, and the wind southwesterly jet that's coming up from the equatorial region into the across the equator, of course, into the Indian subcontinent. It feels the mountain and the winds have to rise, and the ocean begins to feel the winds at that point. So on this side, ocean controls the moist static energy and the heavy precipitation, but on this side it's the atmospheric instabilities that are creating most of the kinetic energy in the precipitation. The other unique thing, of course, is Indian Ocean is very warm, so even in the summer season when the sun is to the north, the ocean is holding on to the marine ITCZ, and from this region we have what are called monsoon intraseasonal oscillations propagating north, bringing eddy kinetic energy, moisture, and so on. But the strong upwelling here obviously reduces precipitation, and you can see that the continuity of the ITCZ is almost completely lost. Okay, so all the action in terms of northward propagation tends to happen here, and we will see that the monsoon depressions are originated from this energy and then going into the subcontinent, bringing up to 60% of the rain during the so-called rainy period or the active period within the season. So the intrinsic time scale turns out to be the so-called intra-seasonal time scale, which is seen clearly here. We are looking at the climatological daily precipitation with particular years like 1972, 94, and 2002. Where there are blue colors, there is above the long-term average rainfall on a daily mean, which is called the active period, and these red regions below are called break periods or mini droughts. So 1972 was an El Nino, 2002 was an El Nino, 94 was near normal, mild warming in the Pacific with a strong Indian Ocean dipole over the Indian Ocean. And you can see anecdotally at least that the break periods are more when you have an El Nino or a deficit year. So you can see the rainfall here. This is more like the normal or slightly above normal, in fact, and you can see this is well below, this is well below. So in these years there are longer and more break periods with shorter and fewer active periods, whereas here there are fewer and shorter break periods with more longer active periods. So the idea is to understand how extremes are manifest in these time scales, active and break. We will see that active periods are where most of the extremes happen, and break periods are getting more frequent and longer, but shorter active periods are getting more extreme. Okay, we'll add those kinds of details. I won't go into the details of the basics of the monsoon because I have lectures on that in other courses. Plus, let's focus much more here on the extremes. So the debate that I mentioned before about the role of the land-ocean contrasts. I don't know why my cursor is getting stuck. I hate it. Okay, here. So the idea is whether the land heating and faster heating and low pressure and ocean slow heating matters. We will see that there are people who believe that's critical, but the main thing to remember is once the monsoon gets set up, the condensational heating and the rainfall actually ends up cooling the surface. So surface temperatures in the monsoon season actually can be colder than the ocean, but the tropospheric heating does drive the cross-equatorial circulation, which is shown here schematically. The argument here is that the elevated heating of the Tibetan Plateau and the sensible heat that is at such a high altitude does contribute to the land-ocean contrast, but this paper by Bill Boos and Jimin Kwang argues that actually the Himalayas just act as a physical barrier to preventing the mixing of colder, drier air with the warm, moist air, and that's more critical. The barrier effect is more critical than the Tibetan Plateau heating. Okay, so this debate will go on. This is from another Goswami and Xavier paper. Maybe Ajay Mohan was also involved in this. What they argue is that the tropospheric heating between the northern box and the southern box over the 200 hectopascal to 850 hectopascal is what is driving the cross-equatorial flow. So you can see that here the so-called delta TT or tropospheric temperature gradient between those two boxes. The meridional extent of the northern box is between 10 and 35 north, and the southern one is between 15 south and 10 north. Vertical shear of the zonal wind averaged over this box is shown in the dashed line here. So you can see the easterly shear that gets set up, and zero absolute vorticity is also shown. But the main point is that when the monsoon onset happens, this temperature gradient changes sign, and then the monsoon season happens, and when the gradient changes sign again, the monsoon withdrawal happens. So this is not exactly land-ocean contrast, but it is tropospheric heating and the ocean tropospheric temperature contrast. Okay. In general, people have looked at various details. We will get into some more, but this is a modeling paper which tries to deconvolve the various pools from the various heating. So it looks at Iranian plateau, Tibetan plateau, and splits the southwesterly jet, which they call the water vapor conveyor belt, into contributions to the South Asian monsoon season, into the North and South branch, and the East Asian summer monsoon branch here. Looking at the Iranian Tibetan plateau, pulling water vapor into the northern branch, and the land-sea thermal contrast contributing to the southern branch of this southwesterly jet, and the Tibetan plateau and land-sea contrast contributing to these East Asian summer monsoon. Of course, the Bay of Bengal, which has lots of convection during the summer monsoon season, also contributes to this pool, the more zonal or westerly direction of the southwesterly jet. The southwesterly jet itself has an intraseasonal oscillation. There is nice work done there by P.V. Joseph and others. It also has a trend in terms of staying more to the north for some decades and flipping to the south, and there is a question about whether that is a secular trend in southwesterly jet or whether it's a multi-decadal mode of the monsoon variability. And then the question is what drives the multi-decadal mode in monsoon, which we will see in the podcast that'll come up next. Okay, so that's a very brief run through the South Asian monsoon. As I said, this is not the course where we're going to introduce the monsoon in detail, but these basics should serve you in terms of orienting you to the issues we will look at. Precipitation changes in terms of their trends and patterns, and extremes changes in terms of their duration, spatial extent, and so on. Okay, so we will look at mostly South Asian monsoon, but we will talk about scaling arguments which are more global, because doing regional scaling turns out to be tricky in terms of looking at the balance between top of the atmosphere radiative perturbations and surface radiation balance, and how this results in moisture variability in the atmosphere, how that results in large-scale circulation change, and how that relates to extreme precipitation changes, which are always local. Okay, especially in the tropics, you have convective systems which are very small scale, whereas there are some differences when you go to mid-latitudes where large-scale precipitation systems produce extremes as well. Okay, we will leave it here and come back to more details on the extremes next.